Hello everyone, I'm Krishna Gade. I'm the founder CEO of Fiddler.ai. We're a startup in the Bay Area working towards the mission of building trust into AI. Today, I'm here to speak to you about a topic of minimizing risks and accelerating MLOps with machine learning monitoring and explainability. A little bit about my background. Before starting Fiddler, I worked at consumer internet companies like Facebook, Pinterest, Twitter, and Microsoft. Particularly at Facebook, I was responsible for creating the feed ranking platform that provided the infrastructure for ranking content and newsfeed, such as people you may know, groups you may like, Facebook stories. As part of that, we worked on increasing transparency around how newsfeed algorithms worked and therefore improve feed quality. Some of this work inspired me to start Fiddler towards promoting explainability and machine learning monitoring for ML teams. And we've been working on Fiddler for the past 3.5 years. Super lucky to have got some great partners, including Facebook, and some great investors who have been on this journey with us for the past 3 to 4 years. So let me talk to you about the most important issue that machine learning teams face today. Model creation has become quite easy these days. People are able to create models with a lot of automated tools. But when it comes to operationalization of machine learning models, it's pretty hard and it can come with a lot of risks. One of the main reasons operationalization is hard is models fail frequently. Unlike traditional software, the performance of models, the quality of models is not completely deterministic. They are stochastic entities which are trained on snapshots of data, and as that data drifts or shifts in distribution, then the model performance can decay over a period of time. And this is an issue that a lot of machine learning teams faced during the pandemic when the whole society got disrupted and all kinds of data sets got disrupted and models that were deployed pre-pandemic into production were no longer effective. There are lots of other problems that models face. For example, models depend on the data that they're being supplied to. The data pipelines that carry features and signals can have disruptions and failures. And this can hurt the data integrity of the features that are flowing into models. And this is very important for machine learning teams to be aware of. Number four is like bias. We are increasingly living in a society where AI products are taking over our lives and they're entering and impacting meaningful parts of our lives. For example, if I'm applying for a refinance, what kind of mortgage rate that I'm going to be approved of, or when applying for a job, will my resume be scanned by a human or a machine learning algorithm? Or when I go to a doctor, how is my clinical diagnosis being done? A lot of places machine learning products are being used. And it's very important these products are not discriminating people with respect to their gender or ethnicity and whatnot. And finally, machine learning models, unlike traditional software, are opaque entities. And you cannot really read up instruction by instruction of how a machine learning model is arriving at a particular prediction. So this makes models really hard to troubleshoot and explain to other stakeholders. And then you see the complexity of models is growing quite fast. It's almost following a Moore's law. For example, every few months we are seeing emergence of a new model architecture that is with lots and lots of hyperparameters, and you actually can see the complexity ballooning in the coming years. And the lack of tools to understand how these models work is essentially coming in the way of modelers to be able to deploy them with a lot of trust. Observing model drift has become a really hard thing today. For example, we've seen cases of machine learning teams deploying models and sort of having models determine the business decisions and the business going awry. And we have seen what happened with Zillow recently, where the machine learning models were being used to predict house prices, and all of a sudden they invested a lot of money in houses that were overpriced. And so there can be many ways that models can drift in their performance. Number one is you can train a model and have a perfectly good accuracy on the training data. But when you deploy the model, you can see that the relationship that is learned between the inputs and outputs has shifted. This is called concept drift. And this can happen, and if you don't observe for it, your model's decision boundary and how it discriminates between positive and negative examples could change. And in effect, in production, it can be making bad predictions. And you can also see data drift, whether that's output drifts or input drifts. Your features, pipelines that are actually supplying your models can actually be supplying data that shifts in distribution and therefore affects the model performance. And some of these drifts could actually mandate model retraining, some of these don't. And so it's very important to know which ones you want to observe properly and where you need to retrain your models. This is why we need model performance management. Model performance management is about tracking the models throughout the ML lifecycle, from the training process all the way to production and then back, where you're not only tracking the models but also their associated artifacts like their training and test data sets, the prediction logs. So you have one single pane of glass that is keeping track of all of these things for your team so that you can get insights from the models. So you can see like what is the data quality of your training data? How is the model looking once it's created from a validation perspective? How is the model compared to like the existing model that's running in production, where you can compare the challenger to the champion? How is the model running in production? How can you monitor for its performance or drift or any outliers that it may be producing in terms of predictions? And then how can you then analyze the model performance overall to see if you can build a better model over time? And so model performance management, by keeping track of all of these assets in one place, helps you improve models over time. And let's look at how it can do that. So when it comes to model drift monitoring, then one of the most important things with drift monitoring is to be able to compare distributions between production and training. So in this case, here is an example of a churn model that is being monitored. And you can see that the churn model is drifting around June 13, June 14th. You can see that the blue line, the dark blue line, is showing that the prediction drift was very close to zero for a while and then started climbing up. It went up to 0.25. And so the way we are computing drift here is we are looking at the distribution of predictions in production on any given day and comparing it with the distribution of predictions in the training set. And then calculating a divergence technique. So for example, in this case, this is using Jensen-Shannon divergence, but you could use any number of techniques that are available in the statistical world to compute these drifts. And when you compute these drifts, you can then characterize whether you're seeing a relationship change happening, whether there is an output drift happening, whether there is a feature drift happening. And any of these things can happen with your models. For example, let's say a bank or a fintech company is using models to approve loan applications. Now, a concept drift can happen when macroeconomic factors change. Unemployment rate increases or Fed reduces or increases the interest rates. They can internally affect the signals that your models are using and their relationship with the model's outputs. Model output drift can change. For example, suddenly you have launched a new lending product or a lending product in a new market, which has a lot more credit-worthy applicants than you had experienced before. Now, all of a sudden, your model is receiving a lot more good credit customers into your system. And so how your predictions can actually then start drifting. And your features can also drift. For example, let's say your income of applicants increases by a certain percentage. Now your distribution of feature in income between the training data and production data can change. And this is very important to observe. And when you observe these things, one of the things that you're looking to do is whether you need to retrain the model or it's mostly a feature drift that you can ignore. And the most important thing you want to notice is when you need to retrain the model. For example, in the case of a concept drift, that can affect the model because it's affecting the relationship between the features and the outputs. So it might require you to update a model. When it comes to a label drift, in cases where the model is working perfectly fine, in such a prediction drift can be ignored and you could continue along with the current model. And you have data integrity issues. That could also hurt your model performance. And you have multiple data pipelines serving these models and they're supplying these signals at scale. And in this case, you can have upstream pipelines, or applications, your front-end applications or your web applications could be producing bad data. When I used to work on data engineering at Pinterest, we used to launch mobile app releases sometimes with bad instrumentation that would produce bad data into our logs that would affect downstream business metrics and our signals into machine learning models. So it's very important to monitor for these things. Here are some metrics that one can use to calculate data drift. You can see population stability index is very, very popular in financial services, but there are other fine metrics like KL divergence, Jensen-Shannon divergence, where you can compare two distributions. In this case, I'm comparing the distribution of FICO score between the production data or live data and the training data and looking at how the densities are distributed. Similarly, you can then attribute the prediction drift to the constituent features, which features are impacting. This helps you save a lot of time in terms of diagnosis. For example, let's say you're seeing a prediction drifting on a certain time segment. Now, instead of going and checking hundreds of features that might be impacting the prediction drift, by being able to attribute the prediction drift to the constituent features helps save a lot of time. And this is a screenshot from Fiddler, which is actually showing which features are having the highest possible impact on the prediction drift. And this helps mine this sort of needle in the haystack, if you may say so. Finally, when it comes to data quality monitoring, it's very important to monitor things like missing values, range mismatches, type mismatches. For example, you can be sending a string instead of a number for a numerical feature. You can be padding extra zeros for, let's say, a feature like salary. You could be changing the distribution by doing that. You could be sending feature logs which don't match with the features that your model was trained with. And this can introduce a schema mismatch. All of these things, when you monitor them, you can actually make sure that your models are not deteriorating in time. And that's is one of the lowest hanging fruit any machine learning team can implement. Finally, when it comes to models that are affecting human lives directly, it's very important to monitor for bias, monitor for how the models are performing within protected groups. So you can keep track of your protected groups, such as the demographic of the individual, age, geography, and then you can try to see in aggregate, not locally, but in aggregate, how the model is doing across these individuals. That way, if a model is having high false omission rates on a certain group or a low true positive rates on a certain group. And in looking at these metrics, you can make sure that your AI and machine learning are working in a responsible manner for your customers. Now, where MPM can help you to monitor how these models work, it's also important to explain how these models work, and so that you can root cause the black box. Here's some interesting technique that has emerged in the recent years in the context of machine learning models and helping them explain how they work. So it's called Shapley value. It is actually was introduced by this person, Lloyd Shapley, in 1953. And this person got a Nobel Prize in economics for this contribution. And it's a very interesting concept. So let me explain how it works in the context of a cooperative game theory. Let's say two people, Alice and Bob, come together to start a company. And now the company is making a certain amount of revenue. Now, let's say we want to attribute the revenue in a fair and appropriate manner between Alice and Bob as their profits. How do we do that? So Shapley came up with this game simulation where he ran this sort of a problem as a game where Alice joins the company first and she starts contributing. So let's say the company starts making $20. So the marginal impact of the company of Alice is $20. And then now Bob joins. And so his marginal impact is $30 because the company has made $50 of total revenue. Now, if you reverse that combination, when Bob joins, the marginal impact for Bob is actually $10. Whereas when Alice joins after Bob, the marginal impact for Alice is $40. So this allows us to basically look at how each person is adding value to the outcome when they join. And then when we look at the marginal impact, when we take an average of the marginal impacts, Shapley called this the Shapley value. And he proved certain nice axiomatic guarantees around it. For example, if a player never contributes to the game, they get like a zero attribution. If there are two players that are almost equal attribution or almost equal impact, they get like an equal attribution. If you add up all the Shapley values, then they add up to the total gain. So these things really nicely apply for explaining machine learning models, because in the context of machine learning model, the model is the game, the prediction is the revenue, and the players are the features. And so now you can say like, okay, let's say you have three features like FICO score, income, and loan amount. And now you want to predict the loan risk of a particular loan application. You can try to then apply a Shapley value concept here to try to attribute which of these features have the maximum impact for this loan denial. Now, there are multiple ways of modeling a feature absence. So for example, let's say if you want to remove income, you can replace it with a value from a certain distribution, and that's called a reference distribution. And depending upon the type of reference distribution that you use, you can actually get multiple Shapley values. This is one of the problems today with like using just one Shapley value because there are many Shapley values behind it. Here's one way the existing Shapley value-based methods work, where they have the game formulation tied to the reference distribution in a tightly coupled manner. And therefore, you sort of can again get attributions, but you're not looking at the model in a holistic manner. And so a normal reformulation that we worked at Fiddler is to decouple these two things, where you have reference samples, and you can have any number of reference samples, and they can then be used for a game formulation. So you can actually get multiple attributions for the same predictions. So now you have multiple Shapley values for the same prediction. Now you can do things like you can compute the mean of all attributions. You can compute the confidence interval of attributions. You can do things like contrastive explanations, so that instead of giving one explanation for a given loan denial, you can say, okay, this person was denied the loan for these reasons when it compared to people of income less than $62,000. Or this is the explanation how when you compare this person to people greater than $62,000 of income. So you can compare with different contrasts and compute explanations that provide a holistic view of how the model is looking at this individual. And this is an interesting work that we sort of published a couple of years ago, that we got the best paper award in one of the AI conferences. So putting all of these things together into a working model performance management system, you can start monitoring issues before they become a problem. So for example, you can monitor for various types of drift, feature drift, label drift, concept drift. You can monitor for accuracy of how the model is doing at any given point of time. You can monitor for data quality issues. You can monitor for like bias in various different protected attributes or combinations of protected attributes. And then you can explain how the model is working on different data points. Explain a single prediction, explain loops of prediction. For example, why was a loan denied for this particular individual? Why was this a particular fraudulent transaction misclassified? Or why a particular customer review was classified as a negative customer review? You can actually inspect these things at scale and understand how the model is working at different levels of granularity. Finally, with all of these insights, you can start analyzing the model more thoroughly. You can compare models like between challenger and champion, in almost like A/B testing of models. You can understand how the model is doing on different segments or like cohorts of populations. So for example, how's the model doing in California versus how the model doing in Hawaii, or different cohorts of data points. And then you can use these insights to improve your training process. Because ultimately, the goal of the MPM is not only to help you create transparency in models, but improve the quality of the models that you're working on. And that's what we are excited to be working at Fiddler towards this mission of building trust into AI and working with great partners and customers. We have been super lucky to have been featured at various different places, one of the promising companies to work. We are actively hiring if you want to join Fiddler in engineering or product roles. And we are also very excited about our partnership with Facebook around PyTorch and explaining PyTorch models using Captum and whatnot. And with that, I'm super excited for this opportunity to be talking about this very important topic. If you want to reach out to me for any questions, you can email me at krishna@fiddler.ai. Or if you want to know more about us, you can also email at info@fiddler.ai. Thank you so much.